This conference will now be recorded.
Great. So let's get started. So I think yesterday we started a discussion with the linear regression example in Python. So you might have understood how the skeleton of a scikit-learn code goes, right? So how can you look up the documentation and how do you understand the functions? What are the different methods available, the attributes? So we have understood how to read the documentation, how to make use of it and start creating predictive models, correct? And also the information that we took is that the same kind of a code can literally be replaced with any predictive model that we want. So the skeleton of the Python code is ideally the same. We just have to change the name of the model that we want to create, and then we have our answer, right? Then the second thing that we started off with is basically the naive based predictive model, right? So we understand that naive based predictive model is a probabilistic classifier. It's only a classification model. Okay, it's not somebody who can do both regression and classification. No, naive based, as the name says, it's a very naive model. Why it's a naive model? Because it's too simple in its approach. It's not very complex at all. It's just trying to use plain probabilities, condition probabilities, and things of that sort. So it's a very naive model. And naive Bayes, why is the name Bayes available? The reason because it was given by somebody called Thomas Bayes, right? So he has been one of the pioneers in this probability area. Apart from Galileo, then this guy, and there are a couple of other people also who came later on. They've been one of the important pioneers in this particular field. The naive Bayes, as the name says, it's a pretty naive model, guys, right? And you're just using plain probabilities here to kind of create a quick classifier. But the best part with the naive Bayes is that it is not so complex like logistic regression, which requires things like optimization. Example, in logistic regression, we came up with coefficients like beta naught and beta 1. How did we do it? We said, hey boss, MLE is going to be the method for you to do it. Maximum likelihood estimation. So you had to kind of solve it using certain optimization methods and all, right? But here we call it as a naive Bayes because it's so simple in terms of creating the model. It's very, very fast. It can work on pretty large data sets. By the end of the day, it's just plain formulas, looking up for numbers and starting to multiply them or normalize for probabilities. So the mathematics behind it is like so simple. Hence, you don't need much of a computation power to work on pretty large data sets. And the results are also not like so fancy enough. I would say it's going to be equal to the logistic regression by the end of the day. It's not a very beautiful model as such because you're just using plain probabilities here. You're not really tracking anything more than probabilities. So that's why once again you gave it a name, something called naive Bayes model. So to understand naive Bayes model, I think we started off a discussion with plain probabilities, right? So we first spoke about the different terms in probabilities. We understood what was random experiment, what was deterministic experiment, what is something called sample space. We spoke about sample point. Then we spoke about something called as an event. We know what is something called trial. Then we know what is something called as, this one, exhaustive cases. Then we know what is something called favorable cases, mutually exclusive events, non-mutually exclusive events, and finally two equally likely cases. I think 10 to 12 different terminologies is what we discussed yesterday, right? Let me reiterate: random experiment, deterministic experiment, trial, what is an event, what is sample space, what is sample point, what are exhaustive events, what are favorable events, what are equally likely cases, then mutually exclusive cases and non-exclusive cases. So like 11 to 12 different terms is what we wanted to kind of understand before we even jumped into the actual probabilities class. Then what did we do? We spoke about the laws of probability. We spoke through this thing, something called as an addition law, right? We did quickly solve some problems too. Then we spoke about multiplicative law. But for multiplicative law, you need to understand something called conditional probability. What do you mean by conditional probability? So you're saying the probability of an event A happening can be estimated provided you already know that the event B has already happened. So this is just P of A. What is the probability that the event A will happen? While this one is, what is the probability that the event A will happen, provided I know that already the event B has happened. So example, there are certain recommender systems that we still see today, which is in existence, which is actually using plain conditional probability. So you guys might have heard something called affinity analysis, association analysis, or something called a priori algorithm. So what happens is, if a customer is going to buy product A, what is the probability that he'll also buy product B? Okay, Walmart did this very famous study, several years back, and they said that, a customer who's going to buy a bread, right? They are more likely to buy brush also. So what are you saying? Hey, if the probability of a particular customer buying a particular product is so much, or if he has already bought this particular product, what is the chance that he may also end up buying another product? I know that he has already bought product B. What is the chance that he's going to buy A? Go back to Amazon, go back to Flipkart. They tell you, right? So when you buy a keyboard, then they tell you, hey, I think customers who have bought a keyboard have also bought mouse. Why? Because it's all into the same category. They have historically seen people buying this particular product, right? So it's more like an affinity here. It's an association between the two products. Even there, you're using what is something called as conditional probability. It's something called as an a priori algorithm. You guys should give it a read, in fact. A priori algorithm or affinity analysis. So this is basically conditional probability. Why did we have to discuss about conditional probability? Because the multiplicative law goes like this. That is, we are saying P of A and B is equal to P of A into P of B given A. That is, the probability that both the events can occur together is equal to P of A into P of B given A. Or the opposite version of it is basically P of B into P of A given B. This is something called as your multiplicative law. From this, you can derive your conditional probability by saying, hey, my conditional probability formula is nothing but P of A intersection B divided by P of B, right? Or the other version of it is P of B given A is equal to P of A intersection B divided by P of A. So you can have, the conditional probability two versions, A given B, B given A, but please understand that they're not equal. I think we did do a problem, right? So we understood that A given B is not equal to B given A. So do not think that they're going to be perfectly matching. No, it need not be. In this case itself, you can see the probability that he'll buy product A, given that he has already bought B, is surely different from buying A versus buying B. Okay. So do not think that, that they're going to be equal here. A given B and B given A need not be equal at all. They need not be matching. Let's first understand that. And then what did we have? We spoke about something called as law of total probability, right? So this is where I think we started off our discussion with something called law of total probability, right? So this was basically your law of total probability, right? Or it is this one here. P of A is equal to summation I runs from 1 till n, P of EI into P of A given EI. So basically the concept is that provided I give you a use case where, there are two bags with you. Okay. So this is more like a first level event, you picking up a particular bag. The two bags may have red color balls and white color balls. So the second level event could probably be you choosing a red color ball. So the point is, somebody getting a red color ball is not directly, calculatable. The reason because you need to calculate what is going to happen at the first level. You need the information at the first level. Using that only, you can go back and estimate what's going to be your second level result. Example like what we discussed yesterday, the first bag is having 5,6 red and white balls, while 3,4 red and white balls in the second bag. What is the chance that somebody might have picked up a red ball? What are you saying? You're saying here the red ball probability is 5 by 11. Here the red ball probability is 3 by 7. That's okay. But they don't come together. You're not picking from both the bags. You're picking only from a single bag, right? So choosing any one of the bat is going to have a 50% probability. So 50% of 5 by 11, 50% of 3 by 7 will become the final probability of you picking up a red color ball. So using the first level information, you're calculating what is going to be your second level information here. While how about the opposite? Using the second level information, can I go back and calculate the first level information? That is exactly when we started off a discussion about something called what? Your Bayes theorem. So both the conditional probability formulas, we just kind of interchanged it and we came up with this one. We said P of A given B is equal to P of A into P of B given A divided by P of B. So this is what is called as your Bayes theorem. So this Bayes theorem is exactly what we're going to be using in creating predictive models, right? So for an example, what did we do yesterday? We were trying to solve this particular problem. So what is this particular problem? Very simple data set. We have a lot of categorical variables. By the way, please understand guys, naive-Bayes models can work only on what? Categorical variables. Right? Even if it's a numerical variables, you need to do something on top of it. I think for every model, it's categorical variables, but still here you have to specify because it's working using frequencies, okay? So it needs to surely be a categorical variable somehow. So you have a categorical variable here, okay? So we have like 3 categorical variables. One feature is what is the sweetness of the fruit? Is it sweet or not? What is the length? Is it long or not? What is the color? Yellow or not? These are the 3 features that were given to us. And then somebody is classifying what kind of a fruit it is. Now what do we want to do? We want to go back and learn some information on this particular data set. So we'll just go back and ask a couple of informations from this particular data set. And then what we're going to do is we're going to ask some questions, okay? Hey boss, I did see a particular fruit which was long in size, and it was not so yellow in color, and it was probably not so sweet. Can you tell me what is the probability that it could be a banana? What is the probability it could be an orange? What is the probability it could have been some other fruit? So what does your Python does here? So the moment you ask this kind of a question, hey, can you tell me that for these features what kind of a fruit it is going to be? He is going to go back and estimate the probability for every classification you have here. How many classifications do we have? We have 3 classifications: banana, orange, and others. While if you recollect back to our logistic regression, it was just 2 people, 0 or 1. So that is called as a binomial logistic regression because there was only 2 people that you were actually kind of classifying. While here, because it is 3 people, you're going to be calling it as multinomial logistic, naive-Bayes model. The multinomial naive-Bayes model. Doesn't mean that logistic regressions cannot become multinomial. Of course they can. You can have a multinomial logistic regression also. Okay. So I'm just saying, so when somebody is saying, hey, I created a binomial model versus a multinomial model, you need to quickly understand that if it's a binomial model, he was just predicting 2 classes, while if it were a multinomial model, it was anything above 2. Could have been 3 classes, 4 classes, 5 classes, we never know. Okay. So multinomial means anything above 2 classes, 2 predictions that he can probably give us is called as multinomial models. Here, what are we doing? We have 3 classes or 3 kinds of targets, whether it could be a banana or an orange or an others. Hence, we call it as multinomial naive-Bayes model. If you were creating a logistic regression model here, it might have got called as a multinomial logistic regression model. So how do we do this? So basically, we need to go back and create a frequency table and start computing what is something called as prior probabilities and likelihoods. What are we going to calculate? We're going to go back and calculate something called prior probabilities and likelihoods using certain frequency tables. Okay. So we'll just go back here. We have created a frequency table which looks something like this. Okay. So what is he saying? He's saying that the types are basically three types for you. It could be a banana, it could be oranges, or it could be others. How many bananas do you have? You have 500. How many oranges? I have 300. And how many others do you have? I have 200 of those. So totally there are 1000 data points with us. You're training a predictive model with 1000 data points right now. Now what we're going to do is, these 500 bananas, out of those, how many of them are long and not long? Hey, 400 and 100 is a distribution. Okay. How many of them are sweet and not sweet? 350 and 150. Okay. How many of them are yellow and not yellow? 450 and 50 here. Similarly, for oranges, there are 300 of those. Long and not long is 0 and 300. Sweet and not sweet is 150, 150. Yellow and not yellow, 300 and 0. Similarly, these 200 fruits are 100, 100, 150, 50, 50 and 150 in the three dimensions that you see respectively. Then what are we doing? We are computing the column-wise total also. Hey, how many long fruits do I have? I think I have 500 fruits which are long in nature. Okay, 500 fruits which are not long in nature. Total makes up 1000. I have 650 fruits who are sweet in nature. 350 fruits who are not sweet in nature, sums up to 1000 again. 800 of those are yellow. 200 of those are not yellow. Once again sums up to 1000 right now here. Right? So these are the different, what do we have? The frequencies we have with us right now. So let me go again through this calculations like what we did yesterday, or I'll probably pose it as a problem to you guys again. So what are we doing? We are going back and calculating something called prior probabilities and likelihoods. So what is the formula we have? Naive-Bayes formula. P of A given B is equal to P of A into P of B given A divided by P of B. Or otherwise, so you're asking a question, hey, what is the probability that it could have been a banana given that I noticed it was sweet, I noticed it was long, and I noticed it was yellow? So you're saying P of target divided by the predictor. The probability that this could have been the classification or this could have been the target, provided these are the predictor variables. These are the characteristics of the fruit. So what are you saying? You're saying, hey, what is the probability that you can even find a banana fruit? Why? Because only if there are a lot of bananas in that particular data set, then there's a very high chance that you can end up with a banana here. But if there are not many, then it's going to be a problem. So probability of banana is a very important thing. Into, now you're saying, okay, can you go back and check, given that it was a banana, how many times did you end up with a sweet, long, yellow fruit? I mean, yellow characteristics. So here the point is, guys, I know it is sweet, long, and yellow. We want to check if it's going to be a banana or not. While here, I call it as likelihood. Why is it called as likelihood? You're asking the question, what is the chances that a banana might have a nature which is sweet, yellow, and long in characteristics? Okay, so you're saying, hey boss, I did find a person who was, tall, black, and he was wearing some coolers. So there's a very high chance, that he could have been some, criminal, let's say. I'm just saying, I'm sorry not being biased, but I'm just giving you some bad example. I was just looking at Avengers, it came in my mind. Okay, so I'm just saying, so there's a tall person who's a little dark in nature. He's wearing some coolers, hats, etc. So your question is, hey, if these are the characteristics, can you tell me if that is going to be this person? Okay, let it be like he is going to be a criminal, or probably let's take it as a detective. He's going to be a detective. If these are the features I saw, what is the chance that he might be a detective? Now you're asking the question, hey, are all detectives having the same kind of characteristics? So you saw a person who's with all these characteristics and you're asking, would he be a detective? But you're going back in your data set and you're asking the question, are all the detectives having this kind of a characteristics? That is what is called as likelihood. So if I see that X is happening, I know that it is Y, while you're asking the opposite fashion. Okay, are all Y's X over here? The causal relationship, right? So in fact, there is a famous study. People say people who are very depressed, they eat a lot and they put on a lot of weight. This is one way. But actually, if you look at the causal fashion, it need not be the same. Not all people who have put a lot of weight needs to be depressed here, right? Some people could be very happy and they still could be eating a lot. We never know. So all depressed people might have a lot of weight, but people who are so, weighing high, they need not be surely depressed. So the causal relationship, is it happening or not? That is what you're asking in this particular part, which we call as likelihood. What is the likelihood that you will see all of these characteristics in a banana? Divided by the probability of you ending up with fruits which are sweet, yellow, and long in nature, right? So going back here, it would have become probability of you finding the target into the predictors. If it were this nature for a given target, what is the chance, that likelihood, divided by probability of the predictor characteristics. So this is what is going to give us the probability of A given B. So going back here, we need to go back and calculate all of these things, correct? This is called as class prior probability, by the way. It's called as class prior probability. This is called predictor prior probability, while this one is called as likelihood. So this guy is called as what? He is called as class prior probability. He is called as predictor prior probability, while this guy is somebody called as likelihood, and this one is called as posterior probability. Okay, he is called as posterior probabilities. So let us just go back to our Excel. We need to go back and calculate all of these things, right? So what do you have? You're calculating your prior probabilities, which is basically what is the chance it could have been a banana. So you're saying, hey, I think we have 500 bananas we are selling out of the total 1000 fruits. So 50% of them are bananas. 300 of those are oranges out of the 1000 fruits I have, and 200 of those are other fruits out of the 1000 I have. So the probability of banana is 50, probability of orange is 30, others is basically 20. Then what are you doing? You're calculating the predictor prior probability, also called as probability of evidence. What is the probability of evidence? The probability of evidence you're asking is, what is the chance I'll end up with a long fruit, a sweet fruit, and a yellow fruit? Can you all give me the numbers for all the three cases? Can you all give me the ratios? Don't simplify it. Give me the ratio as it is. X by Y. Can you give me for all the three cases, guys? Give me a private answer, please. Don't drop a message for everyone. Give me a private answer. Okay. So Vidya, I just told that do not simplify it. Give me the proper ratio, X by Y. I want the ratio. Guys, give me the ratio so that I understand if you're picking the right numbers or not. Yes, Anu, Nizam, Divya, Jishbu, Sanjay, Hassan, Yatender. I don't see answers from you guys. Sanjay, sorry, I saw your answer. Okay, good one, Hari. Good. Good that you've changed it. Okay, Perfect. So we have 1000 fruits. Out of those, how many are long? 500 of those are long. So it's going to become 500 by 1000. So we have 1000 fruits. How many of them are sweet? 650 of those. 650 by 1000. So we have 1000 fruits. How many of them are yellow? 800 of them are yellow. So what is the probability when it's not long? 1 minus this one. What is the probability that it will be not sweet? 1 minus 0.65. What is the probability it will be not yellow? 1 minus 0.8, which is 0.2. So these are your class prior probabilities. These are your predictor prior probabilities, or also called as probability of evidence. So this is also done. Next, I want you all to help me with the likelihood. Okay, I'll just zoom out a little bit. So now tell me, guys, what is the likelihood for this one? I know that it is a banana. That information was shared with me. What is the chance it could have been long in nature? What is the probability? I know that it's a banana already. Somebody has shared that information with me. What is the chance it could have been long? Yes, Hassan, Yatender. Good. No, Divya, no. So we have the information that it's already a banana. So it's not 1000 fruits, it's only these 500 bananas. Out of those, how many of them are long? 400 of those are long in nature. So the answer is going to be 400 by 500. So this is going to be the probability that it's a long fruit, given I already know that it's a banana. Probability of long by orange, quickly, let's go. Long by oranges, 0, good. Long given its others, yes, long by others is equal to 100 by 200, perfectly said. Next is sweet given its banana, good. Thank you guys, thanks for participating, good. So it is going to be 350 by 650, I'm sorry, 350 by 500, right? Then sweet given its orange is going to be 150 by 300. Sweet given others is going to be 150 by 200. Yellow given banana is going to be 450 by 500. Tell me if I'm going wrong somewhere. So 300 by 300. Then it is going to be 50 by 200. Okay. Hope I've done everything correctly, right? Okay. So what we have got is, we have basically got all the likelihoods. So what is the chance it could have been long in nature, given it was already a banana? What is the chance that it could have been sweet in nature, given that it has been already orange? Right? So are all the orange fruits sweet in nature? No, only 50% of those are sweet in nature. Are all bananas long in nature? No, only 80% of the bananas are long in nature. So just because they are long, you cannot call them as banana. There are 20% cases where it has not been long also, right? So this is the point. We have calculated the likelihood. What is the chance it could have been not long, not sweet, etc. You just have to do 1 minus the same thing, right? So when you do the 1 minus the same thing, you will get the not probabilities. Not long given banana, not long given orange, not long given others. 1 minus this one will give you the other probabilities you wanted. Okay. So now what we'll do is, guys, we'll take up a specific case, a specific example. Okay. So the case is, I want to understand what is the probability that it's a banana. That's first case. Then it'll be orange. Then it'll be others. Given that I saw some fruit which was not so sweet, but it was surely long, and it was not yellow. Okay. So what are we saying? I saw a sweet which was actually speaking not yellow, and it is not long, sorry, not, it was long and not yellow. Okay, not sweet, but long, but not yellow. What is the chance it's a banana? Then you need to find what is the chance that it is probably an orange, right? So that's what naive Bayes will do, right? It'll find the probabilities for all the classes. So he's going to find it for orange, then he's going to go back and find it for others also. Then he will say in place of orange it's going to be others, because it's a multinomial naive Bayes, he has to do it for everybody. Okay, so I'll copy these guys and keep it here at the bottom. Okay, so this is question number 1, this is going to be question number 2, this is going to be question number 3, right? So let's go for this particular thing. So the question was probability that is banana given not sweet, long and not yellow. So let's go back. So probability of banana given not yellow, not sweet, but long. You write it as probability of banana into probability of, given it's a banana, what is the chance you'll end up with somebody who is not yellow, not sweet and long, divided by probability of not yellow, not sweet and long. So what would you do? Instead of computing something like this very easily, you can just kind of elaborate it. P of B into probability of not yellow given banana into probability of not sweet given banana into probability of long given it's a banana, divided by probability of not yellow into probability of not sweet into probability of long. So 1, 2, 3, 4, 5, 6, 7. We need 7 terms right now to calculate what is going to be the probability that's a banana given not yellow, not sweet and long in nature. Okay. So we need 7 terms right now. So let's go for the first term, which is probability of banana. Okay. That is going to be equal to this particular number here. It is 0.5. Next, term number 2 is we need probability that it's a not yellow fruit, but given I know it's banana already. So that is going to be equal to where not yellow, but banana, which is this guy here. Okay. So let's hit enter. So he'll give you not yellow and banana. Then not sweet banana, not long banana. Sorry, not sweet and long banana. So not sweet banana is this guy, and then long banana, basically this guy here. So we have got all the numerator terms. 1, 2, 3, 4. We have got. What else do we need? We need the denominator 5, 6, 7. What are the denominator terms? Not yellow, not sweet, and long. So not yellow is this guy, not sweet is this guy, and long is basically this guy. So what we need to do is numerator, let us multiply everybody. So this is equal to product of all of these terms. Denominator is equal to product of all of these terms. Then finally you are saying probability that it could have been a banana is nothing but numerator divided by denominator. That's it. So he's saying 0.34 is going to be the probability right now. So I'll make it as percentage. So you can see it'll become 34.29% that it's a banana. Similarly, you need to do it for orange, right? So or changes that I need to make is for the numerator. So number 1 will be, what is the chance that it is an orange fruit? So this is going to be equal to, where is my orange? It's 0.3. Then I need to pick up not yellow for orange, which is this guy, right? Then we need to find not sweet for orange, which is this guy, and then long for orange, which is this guy. Okay. So I think the numerator is equal to 0. Anything divided by 0. So here the probability that it's an orange is 0. I think we need not even go back and calculate. For others, what do we have to do? Number 1, probability that it's others. This is equal to here 0.2. Then we need all the other probabilities. I think there is one missing here. Probability that it is yellow given other fruits, right? So long 3 is done, sweet 3 is done, yellow was not done. Okay. Okay, so yellow other fruits 50 by 200. This is equal to 50 divided by 200, and here it will basically become 1 minus this answer 0.75. I think we did have it right. Probably it got deleted, I guess. Okay, so coming down here, what are the things we need? We need 3 probabilities, which are other fruits not yellow, other fruits not sweet, other fruits and long. So these are the 3 numbers we wanted, right? 0.5, 0.25, 0.75. Okay, 0.5, 0.25, 0.75. So the product of these people is here. So these are the 3 numbers we wanted, right? So I'll just come down here and I'll paste it. So these are the 3 terms. The product is available here, and the denominator is going to be the same. So I could have just copy pasted. Okay. So we can just copy and paste it as values. Okay. So the denominator is here and the numerator, sorry, opposite. The numerator is here, the denominator is here. Now the probability that could have been others is equal to this one divided by this particular guy. Okay. So I think somebody gave me a point. So did you include the 0.2 in the numerator? 0.2 in the numerator. Was not included. Thanks. Okay. Okay. Now seems to be good. So now what do we have? We have a probability which is equal to 54 percentage. Okay, or 53.57 something. Okay. But we see that when we add it up, it doesn't tally up to 100 percentage, right? So here it's saying 35, here it's saying 53. It will not tally up to 100. It may not happen also. So we are going to normalize it. So how will we normalize? We'll find the sum of all these people. It's equal to 87 percentage only, right? Now we will go back and say, hey, 34 divided by this 87. Hey, this 0 divided by this 87. And then this 53 divided by 87. That's it. So now what you've got is basically your probabilities. So you're saying the probability that it could have been a banana is at 39, while the probability that there's some other fruit is equal to 61. So this is going to become your final classification because he has the highest probability for the given features that you have just chosen. Okay. So this is exactly how a naive-based model will get created, guys. It's very simple. All he's going to do is do all these computations. That's it. And then when you start asking questions to him, something like that, he's going to look up for the answers and he'll start finding the products. And tell me how simple it is, how easy it is to create this model. That's the reason why it's called naive-based. It's a very naive model, not so fancy mathematics, not so good predictive results, but very fine on large data sets. So that's the reason why we call this as naive-based model. And with this, I think we are done with the theory part of our naive-based model. Now tell me, guys, are you all convinced till here? The naive-based model, the formulas, etc. Yeah. Okay. Perfect. Great. So what we can do next is, guys, let's quickly jump into a small use case using naive-based. So the first usage of naive-based was actually seen in email classifier. Okay, one of the first email classifiers that people created, in the pretty inception of all of these problems has been something called as the naive-based model. That has been one of the very first email classifiers that people had created. So let us try to create the same sort of a email classifier here. So what we're going to do is we're going to read some text data. So using the text data, somebody has already classified whether it is a spam mail or it's a okayish mail, normal mail, not a spam mail. We call it as ham, spam and ham. So all we're going to do is we're going to go back and try and understand what is the frequency of a particular word occurring in a given message, and using that particular frequency of a particular word, we're going to assign it to the target and then understand what is the chances that it could have been a spam, what is the chances it could have been a ham. So what is the point, guys? So previously you saw, right? I have a fruit like banana, 400 times it has been long, 100 times it has been not long. Similarly, I have several emails, 500 emails I have, 200 emails are having a particular word, 300 emails are not having a particular word. Same concept. So we're just going to go back and find how many times is a particular word occurring, okay, in all of these spam mails. Then using that, we're going to go back and try and associate saying, hey, if this word is available in a particular mail, it's a spam, else it's going to be a ham, which means it's a regular mail. It's not a spam mail, general mail. Okay. So what I'm going to do is, guys, you can see here, we're going to import some of our standard packages. What are the standard packages you always need? NumPy as NP, Pandas as PD, OS, matplotlib.pyplot as PLT. These are the standard packages. The rest of the packages I'll come back in a minute. So we have imported all our standard packages right now. os.chdir means what? Change your directory. I'm changing my directory to a folder, something called namebase. I'll hit Control Enter. pwd, I know whether it is in the current working directory or not, he will tell me. And os.list directory will tell me what are the files available in this particular, what I would say is folder, right? So I've changed the working directory. I've looked at the present working directory. It has got set perfectly. We have a data set, something called spam.csv, right? I can quickly open it. Just give me a second, guys. It's actually very simple. You can see here. We just have one column which will tell you what is the text here. Okay, so somebody has written free entry in a 2 weekly come up to an FA Cup. Okay, so you can just come back and watch our match is what he's saying. So it's a spam. While see here, free message, hey darling, it's been 3 weeks now, no word back. So he's trying to promote some messenger or something, right? So it's spam here. Similarly, you can see here, urgent, you won a 1 week free tour or something, you can see it's a spam. While the ham mails are what is it seriously how you spell his name, I'll finish my lunch and then I'll come back or whatever it is. So this is the text you have at your hand and this is the classification, whether it has been a ham or a spam. What we are going to do is we are going to read the text. We are going to coin and understand which of these words are very, very important for us. And then we'll go back and start counting it. That's it. So we'll go back and say, hey, read my data set, something called spam.csv. Actually, there are only 2 columns, guys. There are a lot of garbage values and all that's happening. So I'm just going to remove the other people. I'll just create the 2 columns. That is the first 2 columns that I wanted. Go back and look at the head of this one. You can see the first message is a ham. So the second message is ham. The third message has been a spam. He's saying, come back and look at the, FA Cup. Then it's been ham and ham. So this is what we have, the data set with us. Now, what we are going to do is, the very first thing that you need to do is data quality checks. If you remember in our previous class also, we have spoken about it. We need to do some data quality checks. What are some of the data quality checks you do? You go back and check if the columns have got imported in the right fashion or not. You need to check if the columns have got imported in the right fashion or not. So we are saying, hey, data.info. So what is information he's telling us? He's saying, hey boss, I think it's a pandas data frame. You have 5,572 entries and you have 2 columns with you. The first column is class. The second column is text. The class is having all 5,572 entries. So everybody has got filled. There are no missing values. The same thing goes even for a text. 5,572 text is what you have. Everybody has got filled. There are no missing values at all. So the first data has got imported as an object data type. Second guy has also got imported as an object data type, which means they are categorical variables for us now. Perfectly, it has got imported. No, problems in the data types here. What else do you want to do? You want to probably ask for something called as describe. See, he'll try to describe. Okay, so he's saying, hey, the number of classes, the counts you have is 5,572. Here also 5,572. The unique number is basically 2, while here the unique text has been 5169. So it looks like there is a lot of duplicates in your data. Only 5,169 messages are unique. There are a lot of these texts which are actually duplicates for us, which is a problem. You can't give the same sample to the model and ask him to kind of overfit. Okay, so I wouldn't even say overfit. It doesn't make any sense at all. So one of the guy's profile you've already given, you don't want to go back and give it again and ask him to retrain. It doesn't make much of a sense. So you can remove the duplicates. That's what we're going to do next. Then he's saying the top number of times I've seen is this ham repeat a lot. Spam is very less in number. And this message saying, sorry, I'll call you later, right? This is also a very default message that you have seen it top number of times occurring. So what are the frequencies? It is 4,825 times, while here it is 30 number of times. So the frequencies. Okay. So when you looked at the describe, you were able to understand that there are a lot of duplicates right now. We need to go back and remove them. So let's do that. So the number one is duplicate removal. These are all part of your data quality checks. Duplicate removal. So how do we remove duplicates? Very simple, guys. Say data and ask for the text column. So you're saying data, I want only the text column, and we will call a function something called duplicates. Okay, so for series it's not there. Okay, and this is the problem. So for series it's not there. But even for data frame, so or np.duplicates. Just give me a second, guys. Actually, what I'm missing. So oh, duplicated. I'm sorry, guys. The function name was wrong. It's not S, it is D. Duplicated. Okay, so I'm sorry, guys. So the function name was wrong. So it's duplicated. So what I'm actually doing is we are calling this particular column and we are asking if it is duplicate or not. So the function is duplicated with a D here at the last. Sorry, I was using S. So it's a D, okay, duplicated. So what you guys can see here is he's actually checking this column and each and every value. So it's all false, which means it has been unique. Coming down here it's a true. 5,553. This record is saying true, it's a duplicate. Probably it is matching with some other value sitting at the top. Here it's 5,558. This is also true. Probably it is matching with some other record sitting at the top. So wherever it's a true, it's actually speaking a duplicate. Now what we're going to do is we're going to say, hey data dot ILOC, I want you to basically make use of this particular logic. So I wanted to make use of this particular logic and filter out only the rows which are having true as a value, right? So which means I need to do an exclamation. So what we're going to do is we're going to invert the logics, okay, by having an exclamation or tilde symbol. So I'm going to invert it. I'll tell you why I'm inverting, guys. Now see here, I'm saying wherever it's a true, only those records has to be kept. Wherever it's a false, those records has to get removed. And we are saying I want all the columns. Now let's hit Control Enter. So it's .loc. So let's hit Control Enter. You can see that you're left off with only 5,169 rows right now. So let me go again, guys. What we're doing, we're saying data, take up the text column, okay? and please check if there are any duplicates or not. So wherever it's a true, they are basically duplicates. Wherever it's a false, it is not a duplicate, right? So wherever it's true, it is a duplicate. Wherever it's false, it is not a duplicate. Now what we're going to do is we're going to say data.loc. So the Boolean indexing doesn't work in ILOC, okay, because it works with the names. So it's .loc, it doesn't work with ILOC. So we're saying data.loc. By the way, Boolean does work in ILOC. By the way, it's not perfectly wrong when I say it doesn't work in ILOC. So in this kind of a Boolean indexing, you should use LOC. So I think you guys might have discussed it, right? So when I say data.iloc, I can give a Boolean array. This is okay. So I can give a Boolean array something like this. That is okay. But I cannot give a series with the Boolean values on the inside. That is not allowed. So that's why you can't use a ILOC, you should be using a LOC because it will try to match the names of the people who are having true as a value. So you know that name matching is obviously LOC and not ILOC. So coming back here, guys, we're going to go back and say, hey, I'm going to give you a Boolean array right now. Okay. As for the Boolean array, wherever it's a true, I want you to retain that particular row. Wherever it's a false, I want you to remove that particular row. So what are we saying? We're saying wherever it's a true, I want you to retain that particular row. Wherever it's a false, I want you to remove that particular row. That's what he will do. So when we pass this particular Boolean as an input, so we're passing this Boolean as an input, telling him all the columns. What will happen? He will give you only the people who have got duplicated. Can you see? So, okay, I will send it again. I will send it again. It was sent 2 times. It is only the duplicates which will be shown here. Why? Because the ones who are true are actually duplicates, while the ones who are false are not duplicates. So while what he will do, he will retain only the true people who are actually the duplicates, and he remove the false people who are not the duplicates. So what should happen? It should just be the opposite. So the Boolean should basically become opposites. So wherever it's duplicate, it should become false. Wherever it is not duplicate, it should become true. Hence, what we are doing is we are coming down here and we are saying, hey, this logic has to get inverted right now. That's all. The tilde symbol will invert it. So we are saying, hey, I wanted to invert it right now. Now, after inverting, you can go back and save it in the object. Let's hit Control Enter. Now let us go back and ask for data.shape. You can see that we have only 5,169 records and 2 columns with us. The first column is the classification and the second column is nothing but the text data that we have. So we imported the data, we looked at the info, whether there are any missing values or not. We looked at the describe. We understand there have been a lot of duplicates. We are identifying who are the duplicates and we are removing only the duplicates to keep the rest of the people, the rest of the unique values here. How are you removing the duplicates? Removing the duplicates as per the text column here. So you're retaining the non-duplicated ones and you're removing the duplicated ones here. So this is exactly how you filter your data, right? So this is another thing that we basically had to do. So we are done removing the duplicates inside our data now. Okay. What are other data quality checks? Is luckily it is just 2 categorical variables, so you don't have to worry much. But if it were numerical variables and all, you would have tried looking at distributions, outliers, things of that sort. So for now, we need not worry about all those things. It's pretty simple. Duplicate removal alone will do for us. Now tell me guys, are you all okay till here? Whatever we have discussed, the code, the logic, what we're doing, everything, is it okay till here? Okay, perfect. So the next thing what we're going to do is we're going to go back and try and understand the target variable distribution. So what are we going to do? We're going to go back and look at the target variables distribution. So what exactly do you mean by a target variables distribution? So we're going to have a target variable which is categorical, right? We need to understand what is the frequency counts, that's all. So we have a function in Pandas, something called pd.value underscore counts. So it's like the R's equivalent of table. So we have what? pd.value underscore counts. To this particular value underscore counts, what we're going to do is we are going to pass our target column. What is the target column? Is this classification. So what do we have? We have the target column, which is basically the classification. And then we are going to ask, can you please let me know what is the frequencies? He is saying, hey boss, the number of people who are having spam as a value, ham as a value is 4,516 people, while spam as a value has been 653 people. So what do you have? The number of samples of spam has been very less. The number of samples for ham has been pretty high, 4,516. Or otherwise, in terms of distribution, if I divide it, you'll get the proportion. So 87% of the population is basically non-spam males, while 13% of the population is spam males. So what is the distribution? It is 87/13, right? 87% of them are not spam, while 13% of them are actually speaking spam. So what will happen is, in predictive models like logistic regression or decision tree, random forest and other people, right? They might get a little bit biased towards the people who are available in lot of numbers. That is, if I'm going to create a logistic regression model, and if I'm going to give characteristics which is more from a spam male also, your logistic regression will predict that it is a ham male. So you're getting what I'm saying, right? So it's like you're feeding somebody with more, samples of a particular class and very less number of samples for a different class. So when I go back and create a predictive model, my model will automatically be biased towards the class which is very high in numbers. What is the point? When I'm going to feed a model with data set which is having a lot of samples, more of one particular class and less of another particular class, my model may become more biased towards the class which is present in abundance, which statistically, guys, we call as class imbalanced problem. So statistically, what we call it as? We call it as class imbalance problem. So you have a data set which is actually speaking imbalanced. So this is a particular statistical problem which we call it as class imbalance problem. What happens when you have a class imbalance problem? As I just told you, your models may become more biased towards predicting a class which is present in abundance and may miss out from predicting a class which is not so available in abundance. He's going to be biased towards a particular class here because he was fed with more number of samples which were actually speaking very high in number. I mean for a particular class. That's what I mean. I think it's a real world scenario, guys. Why? Because you look at any cases now. If you have somebody like a campaign manager, you want to go back and create a predictive model and understand which of these guys are going to respond, which of these guys may not respond. What will happen? The number of people who are going to respond for the campaign is always so lesser compared to the number of people who might actually respond, or people who may default and non-default alone. Number of defaulters are very less. Non-defaulters are very high in number. So any problem you see, right? So whether a person is having a particular condition or not, yes, the number of people with condition will be less, number of people without a condition will be very high. So class imbalance problem is a very critical problem. There are many methodologies of solving this. I'll just give you all a hint for today, but remind me, we can discuss about this once we jump into the logistic regression problem. We typically use something called as class weightage methodology. What do? We typically use a method, something called as class weightage methodology. That is, while creating the model, right, you tell the model itself that, hey, I want you to give more weightage for somebody who's in less number of quantity and give less weightage for somebody who's available in more number of quantities. Or to kind of keep it pretty simple, you are saying, hey, the error faced by misclassifying a particular data point belonging to a class who is less in number is much more, what I would say is severe for us, rather than misclassifying a sample belonging to a class who is present in abundance. That is, the misclassification error rate when you misclassify a spam should be 10x better, or it should be 10x magnified compared to the misclassification error you may get just for a ham case. Getting what I'm saying? So the error here should basically get boosted. It should get magnified. You should blow it up by 10x times, while here you need not blow it so much. So the error when you commit for a spam sample should be much more bigger compared to the error you commit when you're misclassifying a ham sample. That's what we are saying. So we are going to give it in terms of something called as class weightage methodology. So it's not available for a naive-Bayes model, because a naive-Bayes is just, by the end of the day, plain probabilities. So you can't do anything in a naive-Bayes for a class imbalance. I don't think it should be much of a problem also. But but if you ask me something, if we can do something on this one, no, we can't do anything. So you can look in terms of a plot. This is how the distribution has been. Okay. So what we are going to do now is we need to kind of treat it, right? If it were some other model, we could have done a class weightage. How will you do the class weightage? I can just take up this particular frequency and I will find the inverse of it, 1 by the frequency. Then what I will do is I will find the sum of this guy and I can divide it also. Divide it by the sum of this guy. So now you are saying give 87% of weightage for this one and 13% weightage for this guy. So it is just the inverse, guys. So previously what happened was 87% importance would have got built up for ham, and only 13% weightage would have been given for the spam. Now when you find 1 by the frequency of this one, or the frequency counts inverse, and divided by the sum of it, it will become just the opposite. 87% should be given to spam, while 13% should be given to ham. So this will become what is called as your class weightage. You're going to use this particular class weightage while creating the predictive model. This is a methodology on how you do it. But here in naive-Bayes model, we are not going to use it. Okay, so just remind me once we jump into logistic regression, I'll tell you how to use it. But this is a logic. You're just finding 1 by frequency, and then you're normalizing to come up with the weightages here. That's it. Okay. So this is about a target variable, guys, on how it is actually working. So we have found some EDA. We have done some exploratory data analysis. We see that the target is actually skewed in nature. So we need to solve it with using something called as class weightage here. Let's go back and do a little bit more EDA, shall we? Now what we're going to do is we're going to ask, in the not spam mails, can you tell me which of the words are occurring any number of times? So what are we saying? We are saying in the not spam mails, can you tell me which of the words are occurring many number of times? This is what we are asking. So he's saying there are words like to, you, I, the, a, I, and, in, you, for. These are the different words which is occurring many number of times. Actually, it's not right. right? These are not the correct words which will help me classify whether it's a not a spam or not. So this is completely wrong. I should be removing all of these things, right? Similarly, when we go to the spam mails and let's check which words are occurring many number of times, I think it's the same thing. You, call, have, from, and, right? Then you have what are the last? Free. Free seems to be okay. So these are the different words which are occurring many number of times here. I don't see much of a relevance. In both cases, I can see that these people have been occurring many number of times. So what do you call them as, guys? This you, me, and other things. Do you call them as adjectives? Sorry, not so good at the grammar part. What do you call them as? Adjectives? Are they? Things like the, you know, uh, to, me, those kinds of words. What do you call them as, guys? Prepositions, adjectives. What do you call them as? I don't know. Anyways, I don't see any answer from anyone. Is everybody poor like me? Articles, is it? Okay. Okay. Thanks, Sanjay. Thanks, Anu. So you call them as articles, is it? Okay. Oh, adjectives is something like this one. Oh, describing a thing. So it's articles, is it? Okay. Articles. Perfect. So these are basically articles, right? So articles which are common in both the cases. So it doesn't make much of a sense for us. Ideally, we should be removing those things. Okay. So what we will do is we'll go and do some pre-processing on the text here. Okay, so there's a little bit of NLP also involved, natural language processing. We're going to remove all these things. In fact, what is prepositions then? There's also preposition. Right? What are prepositions? This one, she arrived after dinner, things of that's what. Or temporal relationships or mark various semantic roles. Okay. Even prepositions, right? Articles, prepositions. So you basically have to remove all of these things. Yeah, pronouns also you can do it, right? You know, very tall or dark red, those kind of things. So pronouns also you can start removing it. Yes, right? That's what you call pronoun, isn't it? If I'm not wrong. I don't know. So whatever it is. So you need to be removing all of these kinds of words. So words that doesn't make much of a sense, which is very common. Okay. So I'll do my level best in this particular pre-processing. I'm not doing a very fancy pre-processing, just simple things. Like we're going to remove some punctuations and all. Okay. So we have a package here, something called string. In this package, when you say string.punctuation, it can give you all the punctuation marks that people would use. Can you see here? These are the different punctuation marks. So I can clean all of these punctuation marks right now. Okay. So what we can do is, so we can just go back and say, hey, give me a text. Okay. Then what we're going to do is we are going to iterate over this particular text. Example, if somebody is saying hello.world, comma, good, exclamation of morning. If this is a text that somebody is going to give us, we are saying, hey, I for I in text. What will happen? He'll iterate and he'll pick up each and every letter right now. Can you see? He's picking up each and every letter for us right now. Now what we can say is, we can say, hey, I want I for I in text, it's okay. But give it a condition. You have to print I only if it is not in this particular text. Okay, so we are saying I for I in this particular text. Now we are giving a condition only if this I is not in, okay, only if this I is not in any of these punctuations here. So what are we doing? We are saying, hey, obviously I want you to print the I only as usual. For I in text, that's okay. But print them only if this I is not in this any of these punctuations that we have. Let's hit Control Enter. Now do you guys see? He has removed all the punctuations. It is pretty clean. We just have the word with us right now. Now what can you do? You can just use the function something called dot join. So he'll just join everybody with nothing in between them. If you give a space, he will join everybody with a space between them. If you give a tilde, he will join everybody with a tilde between them. So the join can basically take any iterator and it can join all the elements in this particular iterator using this particular separator. Now you're saying no spaces, single space, double space, triple space, or a tilde, right? You can ask them to join using anything, but we are saying do not join with anything. So now you get your word. Now later on what you can do is you can go back and remove certain stop words and all. Example, going back up, we have a library something called NLTK, okay? NLTK is not part of the Anaconda distribution, guys. You need to go back and install it separately. Okay, so there's a particular procedure by which you do it. So please Google it and check it how, or else please let me know if you're facing some issues. So NLTK is not so easy in installing. So you can't have it as part of your Anaconda distribution. You need to install it. Now we are saying from nltk.corpus, that's a module on the inside, we have something called stop words. Go back and check what are the different stop words we have. Let's print all the stop words. So there are a lot of stop words with him. I'll say list of these stop words. Okay, not iterable. Why? I for I in stop words. Okay, why should it not be iterable? There is a method for looking at these stop words. Okay, fine. So actually you can look at all these stop words. So else shall we just go here and check? He's saying D, NLTK, corpora, and stop words. So let's go here. So D, NLTK, corpora, okay, it could have been a hidden file. Okay, we have it here. Okay, so it's here. Then here stop words, right? Let's go to stop words. Then we have English. So shall we open a notepad so you guys can see? Or word. Oh, WordPad. You're also strong. Okay. Okay, now you guys can see. So we have all of these words that we've been talking about here in terms of something called stop words. Can you see? I, me, my, myself, we, our, ourselves, you, your, yourselves, him, choose, why, what, not. So you have all of these words here. Is, right, weren't, wouldn't, don't. So you have all of these words available here, isn't it? Anywhere, then, above, after, below, to, from, up, down. So this library is actually having everything. It'll have all the stop words saved right now. So all you need to do is, once again, you just need to write some kind of an iterator and check if these words are not available there or not. Okay. Say for an example, what you can do is you can take up the text you have. So you'll have a text something like this, isn't it? There will be some spaces between them, between each and every word. So you can say text dot split using the space between them. So you get each and every word here. Or from NLTK, you can import something called word tokenizer also. Okay, I don't know where it will come in NLTK, which library it is. Okay, even in NLTK, there is something called as word tokenizer. Even that tokenizer can do it for you. So there's something called word tokenizer. There is something called sentence tokenizer, etc. So this one will be very simple. You can just split it using a space between them. You have got all the words. There is hello, there is world, good morning. So we'll do the same thing. I for I in this particular guy. Okay, so what is he going to do? He's going to print each and every word again. Print it only if it is not in this particular stop words. That's all. Okay. So what is the problem here if it is not in stop words? Oh, okay. I should say words.english. Sorry, guys. Yeah, I was just wondering. We didn't give the language yet, right? Okay, now should be good. Now if I hit Control Enter, you should be able to see. Can you see? These are the different stop words. So now what we're saying is, we're saying, I wanted to print this particular word only if it is not in this particular stop word. Let's hit Control Enter. Okay, so what is he saying? If is missing, if not in this one, if I not in this one. Okay, so you can see here, he's checking his hello world, good morning, etc. Okay, probably in fact we need to lower it. Even that is another thing because it's all in lower cases. So he's checking the lowercase version of it. It still seems to be fine. Words like hello, world, good, and morning, they're all pretty okay. It's not a stop word, is what he is saying. Now, say for an example, we'll keep where, when, I, am, then probably, don't, things of this sort. Now we'll go back and ask him to check it. Now, can you see? He has removed where, when, I am. He has kept don't alone here. So these are the different stop words you will have, and he was able to remove the stop words right now. So that is the second thing that we're doing. So the first one is we removed the punctuation, right? That is the first thing we did. The second one was we started removing all the stop words here. Another thing people typically do is they do autocorrect. They want to check the spellings and all. So there's a library, something called spell. So using this particular guy, you can do it. Okay, so in fact, there is another guy, something called autocorrect. Even this guy can help you with that. Okay, so these libraries can help you rectify the spelling of a particular word also. Then you can replace that new spelling in place of that particular word. Because sometimes when somebody is going to write when with an extra E, right, what will happen? He will not be able to understand. He says that I think it's just another word. But you know, it's a spelling error. If you leave it to autocorrect, he can, change it for you. He can make it as when with a single E. So even autocorrect is another thing that we typically do. Okay. And I think this pretty much summarizes it. This is like the basic text cleansing that we typically do. Okay. So you guys can see here, that's exactly what I've written in the form of a function, guys. We're saying process, give me a text. I'm going to remove the functions for you, sorry, punctuations for you. Then I'll construct the sentence back. Then I will remove all the stop words. Then I will return all the clean words for you in as a result back. So this is the process text that we have, a function which will do the work. Now what we will do is we'll just go back and say, hey, data of text, I want you to basically apply this particular function on this guy. So we are basically saying process text is the function which you have to apply on this particular guy. Control enter, he will start cleaning each and every text that you have here. Okay, it's actually cleaning it. So what we should have ideally done is we should have saved it back there. Okay, so let me stop this process. So I'll just hit Control Enter. He's going to clean this particular text and he will save it back in this particular column itself. Okay, it's taking some time. Okay, I think it's got completed. It's good. Now let us just go back and check what are the frequent words for not a spam. Okay, so he's asking string instance, but we gave him a list. Okay, data of text, it's a list. let me do one more thing, guys. I think we need a list by the end of the day. Okay. Um, okay. Okay. So what I'll do is just give me 2 minutes, guys. We need to run this. So what happens is that function, I've written it for a string based thing only. Okay. So process text to. So actually this function, we have written it for a string only. So what I'm doing is I'm just creating another function duplicate of it, which will just convert it as a string by the end of the day. Okay. Now let's go back and check our data. So what are the words, guys? You can see here. Okay is a word that's coming many number of times. Then you call is a word. So these are all ham, okay, not spam messages. Then yup, then okay, then I'm home, I'm leaving house. Okay, I think in fact I made a mistake. We should have given it with a space here. Okay, just give me a second, guys. Once this completes, it'll be perfect. Our results will be perfect. Okay, now let's check it. So he's saying no, like, come, time, call, day, want, going. These are the different words that is available in non-spam messages. Okay, let's go to the spam messages and let's check what are the different words he's having. He's saying call, free, mobile, you, claim, price, stop, contact, reply, service, send. Now it seems to be okay, right? He's saying what? Call, free, mobile. He's saying claim, price, text, right? Text which is like lowercase, uppercase, everything is happening, right? Lowercase u, uppercase u, and then what do we have? Service, send, right? So these are the different things that he's having actually. In fact, you can do another thing. We could have even lowered while converting these text here. You could have kept it as lower also. So while cleaning, finally you can just lower it and keep it. I think I missed this. Okay. So that's it, guys. So this is what I wanted to tell you all. Just give me a second. I'll just create this function again. Let's run this. Meanwhile, I can remove this and also say delete data of text2. Okay. So the next portion is actually speaking the meatier part of this entire process. Okay. So now let's go to data.head. I think the two columns are with us. So you can see here, class is here, text is here. So in the first message, these are the different words you have come up with. The second message, these are the different words we have. Third message, these are the words we have. FA, cup, final, then free is here, weekly is here. Okay. So I think we're good. Till now, we have cleansed the data also properly and everything seems to be fine. Now it all stands on the creation of this one. You just have to start creating your model right now. That's it. So what we're going to do is, guys, we're going to start creating our predictive model. So the methodology that we're going to use is something called bag of words model. Okay, the model is basically called as bag of words model. It's a concept for creating a model using NLP data. So it's called as bag of words model. So the way we are going to create bag of words model is pretty simple. Here, before even I jump into this bag of words model, let me tell you something else. We need to split our data set into something called train data and test data, so that you can create your model on somebody and you can evaluate your model on somebody else. Okay, so we have this concept of something called training data set and testing data set. So what we have right now is we have one giant data set with us, isn't it? So we have one giant data set with us, where the first column is your predictor and the second column is basically your target, right? Just give me 1 second, guys. Yeah. So the first column is basically is your predictor. Okay. So the first column is your predictor capital X, and the second column is basically your target capital Y, right? So now what we're going to do is we're going to split the data set that was offered to us into two pieces. The first piece will be a training data set. The second piece would be a testing data set. That is, here it will be 70% of your entire data set, and here it will be 30% of it. Otherwise, people also keep 80% here and 20% here. Why? Because you'll go back and create your model on this guy and you will test on this guy. I think we discussed this in the last class, right? So it should be okay. So we create the model on 80%, we test the model on 20%. It's called outsample testing. While if I create my data set on the entire data, create my model on the entire data, and I test my model also on the same data itself, that is called in-sample testing. So we have outsample testing, basically a certain part of the data which was kept outside, not part of the predictive model creation. You're using it for testing the model. That is called as outsample testing, while the data set on which the model was created itself is used for testing the model. That becomes the in-sample testing. So what we're going to do is we're going to divide a data set into 70-30 or 80-20 right now. So I'll just go back and put a split here, and I will say that the top portion is nothing but my training data set. The bottom portion is nothing but my testing data set, where this top portion will be used in the creation of my predictive model, and the bottom portion will be used in the evaluation of my predictive model right now. Okay. Then what else do you do? Once you have the training data set, we also know that typically we divide it as targets and predictors, isn't it? We do a vertical split like this also. We say, hey, even the training data set, okay, I have split it in row wise and I got a certain number of samples. You split the training data set itself horizontally and tell that this is predictors and this is targets, isn't it? So this will become your training data sets predictor. This will be called as training data sets target. This portion will be called as testing data sets predictor and testing data sets target. Training data sets predictors, one object, you will create object number 1. Training data sets target will become object number 2. Testing data sets predictor will become object number 3, and testing data sets target will become object number 4. So these are the 4 objects that you're going to create right now. And how will you start using? You will say, hey, I want you to fit this particular model using training data set predictor against training data set target. So what will he do? He will create the predictive model for you, right? Then what will you do? You will say model dot predict predict only using the testing dataset predictor. So you're passing right now. You're passing only the predictor, and he will start giving you what is called as predictions, which is your y cap. He will give you the y cap. But what do you already have with you? You already have the test y with you already saved, isn't it? Now you will compare. What is my prediction and what was the original true value? Are they matching together or not? What is the amount of accuracy am I seeing? This is exactly how you can evaluate your predictive model right now. So training dataset predictor, training dataset target will be used in the creation of the model. Once the model has got created, this portion is sent on the inside to get predictions outside. Then this portion is used for comparing the prediction and the true value. So this is exactly how the four objects will be used here, guys. So going back, you can see here, we have a function, something called train test split in scikit-learn. See here, scikit-learn dot model selection train test split. What will he do is, he will take only the predictors separately and only the targets separately. What is he doing? He's saying, give me the capital X, the predictors only. Give me the capital Y, the target only. What will I do for you? I will create a test data set, which is 20% of it. So 80% will be kept as train and 20% will be kept as test. So you guys can see here, capital X will become train X and test X. Capital Y will right now become train Y and test Y. So let's hit control enter. You guys can see here, data of text dot shape. What is the shape? 5169 records. So 5169 records is what we have, a single predictor column. But now, after I say train underscore x dot shape, you can see it is 4135, whereas test underscore x dot shape will give us the remaining, which is 1034. So this 5169 and 80% of this guy is what? 5169 times 0.8. 80% of this guy is 4135. Can you see? 4135 records was used for training, while 1034 records is kept outside for testing. Same goes even here. Data of class dot shape. You can check. There are 5169 labels. So many samples you have, one target column. But that became train Y, which is 4135, and test Y, which became what? 1034. So this entire target column of 5149 or 169 became 4135 for the training data set and 1034 for the testing data set. So you are able to divide the X and Y into train X, test X, and train Y, test Y right now. Now tell me guys, any confusions on this particular portion? What exactly are we doing? How are we dividing it? Are you all okay with this particular function? Because this is a common area where I see people get kind of confused. Are you all okay with this particular portion? Yeah, clear? Okay, so the question is, this split, is it mandatory for all the models as part of the evaluation? So there are different evaluation techniques. So this is something called in-sample testing. Typically, similarly, people do something called cross-validation. Okay, under cross-validation, you have different types like k-fold, stratified k-fold, repeated k-fold, and many other things. Even then you have time-based validation that you can do. There are a lot of validation techniques available, and even bagging is another validation technique. So this is one of the validation techniques available here. This is the simplest validation that you can do. Okay. This is one of the simplest validations that people can do, something called train test splits. Okay, so Hari has a question. So here, the classes ham and spam are also getting equally split into train and test set. Yes. So actually, what is happening is the way you need to think of it is like this. Let's go here. Okay. Suppose let's say I have 25 rows. I'm going back here. I'll paste it here. 25 rows. Okay. So my total data set size is what? It is 25. Somebody wants a train and somebody wants a test. 80% of 25 is 20 records. Then you have 5 records. So what you will do is you will first randomly sample 20 records. So I will just probably go and choose these people. Probably I'll call them as the 20 records. So this portion will become your train data set, and the rest of the portion will basically become your test data set. That's all. Randomly sampling it as train and test. Then what do? You say that these people are my X. So I will just copy and I'll paste it here. So this becomes my X, while this becomes my Y for those people. Similarly, these people are my X and these people are the Y for me, right? So what will you do right now? You will create a name-based model saying, hey, this is the data set, okay? This is going to be your capital X. So you will tell him, hey, this is your capital X. You should use these predictors. This is your Y, which is your target. I wanted to create the model using these people. Then you should start asking all these questions. Sweet long yellow, what is your classification? You are saying others, is it? But actually it was a banana. So you misclassified. Then you're asking, sweet not long and not yellow. Did you say orange? Okay, I think it was orange here. So you will take 1 right now. So similarly for all of these people, you start giving classification. He's saying others, he's saying orange, he's saying banana, then he's saying others again. So others and others matching, orange, banana not matching, banana, orange not matching. Yes, it is matching. So out of the 6 samples you kept outside, 3 of them were correctly predicted, 3 of them were not correctly predicted. So you have a 50% accuracy right now. Now getting it, how it's working? The splitting of train, test, target, predictor. So if this is your data set, this is how it will get split. So 80% of the samples will be kept here. 20% of the samples will be kept here. Then you're saying, okay, of the 80%, this is the predictor. Of the 80%, this is the target. Of the 20%, this is the predictor. Of the 20%, this is the target. So this is how they're basically getting split here. Is it okay, Hari? Convincing? Okay, perfect. Let me leave it here. Okay. So going back to the Python code, so we were able to split this particular data set, correct? Next, what do we have to do? We basically have to pass all of these features to your predictive model. Okay. So the way we are going to do is, guys, we have this concept of something called bag of words model. What do you mean by bag of words model? It's very simple. In a bag of words model, we typically create a data set, something called TDM or DTM. It's called as term document matrix, or also called as document term matrix. So in a bag of words model concept, we create something called TDM or DTM, guys, term document matrix or a document term matrix. So what he will actually do is, he will take all the words that is available in your data set. That's all. He's going to say, hey, there's a word like free, there is a word like bonanza, then there's a word like offer, then there's a word like morning, then there's a word like home, coming, cab. So there's a lot of words available inside your entire data set. So in the first message, it could have been a spam. In that message, free was used 5 times, bonanza was used 1 time, offer was used 10 times, while other words were all 0. Then you're saying in the second message, it's a ham probably, All of these words were not at all used, but here morning was used once, home was used 2 times, coming is used 3 times, cab was used 2 times. So you're going to create a frequency matrix like this, guys, where the documents will be here on the rows and the words will be on the columns. So document term matrix that you're going to create right now. It's a document term matrix. You're going to create a frequency matrix, something like this next. Then that will be passed on to the multinomial model and he will be able to find all the probabilities, etc. So let's go here. You can see we have in scikit-learn something called count vectorizer. Where is it coming from? From scikit-learn dot feature extraction dot text, there is something called count vectorizer. As the name says, what is he saying? I'm going to count it and I will convert it as a vector, a particular sample for you, a set of columns for you. So we are saying cvec is equal to count vectorizer. And then we are saying, hey, can you please fit and please understand what is the total dictionary that you have? What are the different words available in my data set? So let's hit Control Enter. What he's actually doing is he's actually learning this entire data set. Okay. So what's happening? I think I should have passed it as a string only. So dot join. Just give me 1 second, guys. Once it completes. What is not completed? Okay, so what actually this fit is doing is it's learning all the different words available in the data set. It's compiling a dictionary right now. So once it compiles a dictionary, then it will be able to transform it as a DTM matrix for us here. Okay, so let this get completed. The moment we complete, then we can just split it as train and test. We can fit it so that he can learn the dictionary. Okay, it's all done. So we have split it. We are calling count vectorizer. We are fitting it. He has learned it. Okay. Then now we will say we will ask him to basically transform this training data set. So we'll go back and look at the features. You can see he's saying I have 4,135 rows, so many documents with me, and there has been 8,162 different words available in this particular data set. So what is he saying? 4,135 documents have been there and 8,162 words are available. And he's giving you the counts on the inside. Okay, I don't really want to convert it as a matrix and show you to you all. It's going to exhaust the buffer here. In fact, it has saved as something called sparse matrix. Okay, it's a form where it'll try to compress the data set and it will save it. Okay, it's called compressed sparse. You can see here. It's actually compressing it and then saving it for us. So 4,135 documents are there and 8,162 words are there. So many rows and so many columns, and he's counting the words available on the inside. Now what we will do is we'll go back and import something called multinomial NB. So scikit-learn.naive-bayes import something called multinomial NB, multinomial naive-bayes. We'll say, hey, this is the model instance. Fit the model with these predictors and this target. So he's able to predict and he's able to create everything at the back end. Okay. Now what are you saying? You're saying this is the test data available with me. I don't think you can make use of the test data directly. This should also become a DTM matrix. So you can see here, the test data set should also get transformed. So I can call it as the test data sets features. Is nothing but take up the test data sets predictor and transform it right now. Look at the test data sets features. He is what? 1034 documents but with the same 8,162 different words he has learned. So these are the test features you will have. Now these predictors, you're sending it to the model to come up with something called as the predictions. You started predicting whether it's a spam or a ham for these 1034 documents you've kept outside. But the original values for these 1034 people has been this one. What can we do? We can just ask, hey, test underscore y is a true value. Check whether it is equal to the predictions or not. It'll give you true and false. We'll find a sum of it. It'll tell you how many people were correctly classified. So 1016 people were correctly classified. Out of 1034 number of people, you have an accuracy rate of 98% right now. What are we doing? We're saying, hey boss, this is the true value and this is the predicted value. Can you please let me know where the true values and the predicted values are matching? Sure, I can do it. Can you tell me how many of those? 1016 of those are actually matching. Out of the 1034 records we have, you have a 98% accuracy right now is what we are saying. Okay. So you can look at the classification report also. He'll tell you there's another detailed version of it, or you can create a confusion matrix like this. I'll talk about all of these things probably in another class. Okay. So we are creating a classification report. There are a lot of metrics available here. And here it's a confusion matrix. It will just tell you what you predicted, what is original value, did they match or not. So 124, 892, you can see. So 892 people were ham and you also predicted as ham. 124 people were spam, you also predicted perfectly as spam. So how many of them did you correctly classify? 892 plus 124, 1016 people. How many people did you misclassify? 5 plus 13, 18 people you have misclassified. So these 13 people, they could have been a spam, but you predicted that it was a ham. And those 8 people, they could have been a ham, but you predicted as spam. Right? So 892 guys, right? They would have been a ham, you predicted as ham. So you did the right job. 892 people, ham as ham, correct. Similarly, 124 people, spam as spam, correct. So 124 people, spam as spam was correct. But the 13 people, they could have been a spam, but you predicted as ham. And 5 people who were actually ham, you predicted as spam. So these are the correct predictions, but these are misclassifications you have done. That is what actually the confusion matrix is telling us. I'll deep dive into all of those things probably in another class. Okay. So confusion matrix and what are these different metrics, sensitivity, specificity, precision, recall, F1 score, all of these things we need to deep dive on the logistic regressions use case that we're going to solve. It's all here. Okay, so we're going to deep dive and discuss about all those things. Okay. So that's it, guys. I think we have quickly created a naive-based model and we have seen the performance of the model also seems to be good enough. He's able to relate all the keywords or the words available in the message and he's able to tell that yes, it's a spam and a ham, right? So any questions till here, guys? Are you all comfortable with this use case? Are we good till here with this use case? A quick spam classifier using naive-based model. Yeah. So count vectorizer, multinomial NB. Why are you transforming even the test data set? Then you're passing on for the predict function to get predictions. Then you're checking the predictions in the true value. All of these things, is it okay? Following the Python code? Okay, awesome. Hassan, is it fine? Savik, Sanjay, Rakesh, Manjeet, is it okay? Jishbu, Divya? Okay. Okay, then. So let's take probably a 13-minute break. Okay.
This conference will now be recorded.
Okay, so just recollecting back on what are the different things that we have learned for today. I mean, at least for this entire, 2 weeks. So we started with linear regression. We understood concepts behind it. We spoke about something called R square. We have seen a use case in Python on how to solve it. We did it in R also. We did it in Excel too. So which means linear regression should be good. Number two, we jumped into logistic regression. We have completed 90% of the theory is what I would say. I've told you how does a model get created. So similar to R square, there is a metric there which we should be discussing. We have something called deviance, then Akai case information criterion. So that is an open item, and even the use case for logistic regression is an open item. Okay. Then third, we jumped into naive Bayes model. We have spoken about probabilities. How does naive Bayes theorem works? Then we have seen a use case of it, the Pythonic based example. So which means by this, naive Bayes is also done. Okay. So as per a schedule, the next model was actually speaking KNN, and then later on it was clustering or k-means. Okay. But what I thought is, I'll just take a small detour. Let's go to k-means. Why? Because k-means and KNN are very, very similar. If I tell you what is k-means, right, I can just tell you what is KNN in another 10 minutes. Rather than working on k-means for half an hour, then coming back to k-means and spending 2-3 hours is not the right thing to do. So let's jump into k-means. Sorry, guys. So let's jump into k-means, and then we can go back to KNN and we can discuss, how exactly is k-means and KNN a little different. And then over to the next week or something, we can just start discussing about use cases for both and even into logistic regression. So you know what is going to be the agenda for next week's class also, right? So k-means we'll continue. We'll discuss KNN. We'll see use cases for both. And then we'll see the use case for logistic regression, which is pending, since yesterday. So now jumping into this clustering algorithm, guys. So what we have done till now is we have discussed two types of algorithms, right? Number one is we have spoken about something called as regression. Number two is we have spoken about something called classification. So when it comes to supervised learning, we have two. One is we have regression. Number two is we have something called classification. And we have kind of discussed use cases. I would say even algorithms for both the cases. We have linear regression, we have logistic regression, we have naive-based classification model, right? Now what we're going to do is, guys, we're going to jump into an unsupervised learning technique, something called clustering. Okay, so what we're going to do is we're going to jump into an unsupervised learning technique, something called as clustering. Let me give you all a small background about a particular problem we're going to solve. Okay, so let's come here. You can see here, guys, what we have is, we have, let's say, a massive retail chain, okay, who's running 49 different stores. So what do we have? We have a retail chain who's actually running 49 different stores. This objective is something called as market segmentation problem. So what is this objective, or what is this use case? It's called as a market segmentation problem. What do you exactly mean by a market segmentation problem? Pretty simple, guys. So we have 49 different markets here, isn't it? 49 different stores or 49 different markets here. For each of these markets, we have different features, we have different characteristics. So a market like Albuquerque versus a market like Atlanta, they have a lot of difference, because in Atlanta you see that 67% of the population has been black, while only 3% of the population has been Albuquerque. I have been in Albuquerque. While 35% of them have been Hispanic in Albuquerque, while only 2% of them are, Hispanic in Atlanta. Look at the Asian population, it is 2 and 1. Doesn't seem much of a change. The median age group of people living in Albuquerque is 32, while the median age of people living in Atlanta is 31. The unemployment rates have been 5%. The per capita incomes has been 18 and 12 respectively. So the point is, guys, we have 49 different markets with us, and we have the characteristics of each of these markets. We have a lot of MEVs, we have a lot of demographic data, things of that sort. If you recollect back to our very first class, right, if you compare it with something called SNS, which is social network service, where we wanted to segment our students into different segments. So we have a lot of students, they have different likings towards different topics there. We wanted to segment the students into different categories, right? Similarly here, what we want to do is, we want to segment the different markets into different groups here. So this will become one group. This is another group. This is going to be another group for us here. So this is going to be a final segment for us. We are trying to segment all of these markets into 4 different groups or 5 different groups, 6 different clusters, 7 different clusters. We basically want to segment all of these samples saying, hey, I think all of these markets are pretty similar to each other. Or I think all of these graduates are probably similar to each other. Or all of these customers are very similar to each other. I think all of these bugs are very similar to each other. You're basically trying to understand a point-to-point similarity. So the record number 1, how is he similar to record number 2? How is he similar to record number 3? Record number 4? So row-wise, you're computing how much is the similarity between all of these people. Then similar people, you're basically noting them down. Let's talk about another example. In a recommendation problem, if you remember, we spoke about 2 kinds of recommendations people typically do. Sorry, guys. Yeah. So in a recommendation problem, there are 2 kinds of recommendations people typically do. One is a user-to-user based recommendation. Number 2 is a product-to-product based recommendation. Or the third one, something called collaborative filtering, which will combine both the things together. User to user, product to product, as well as collaborative filtering, which is a hybrid version of it. So since a long time, guys, what people were using is, they were using something called as vector space model. Okay, for this recommendation, pretty long back, some of the basic models that people created was something called vector space model. What do you mean by vector space model? Say for an example, I have customer number 1 who basically bought Coca-Cola at what, probably 2 products a day. Then something like bread, he bought 5 products a day. Then probably eggs, he bought 20 in number. While look at the second customer, he has bought 3 Coca-Cola per day, 6 breads per day, 25 eggs. While the third customer did not buy any products, probably eggs alone, he has bought 5 products here. So what do you have? You have the 3 different customers here. The first guy, the second guy, and the third guy. Now what I will do is, guys, I'll take a 3-dimensional plot right now. So we'll take a 3-dimensional plot, something like this. So we are saying X is nothing but the number of times he has bought Coke. Then this is going to be the number of times he has bought bread. And the third one is going to be the number of times he has bought egg. What is the first vector? 2, 5, 20. So 2 Cokes, 5 breads, and 20 eggs, right? So I can probably plot him somewhere here. Okay, so it's not exactly right. So let me plot him here. Okay, 2, 5, and probably 20. Okay, so let me try to plot him here. Okay, so this is exactly where he has bought 2 Cokes, and this is where he has 5 breads and then 20 eggs. Okay, so we have this particular vector here, guys. Okay, so I'll go and redraw it again. So probably this guy. So this is where your customer number 1 is there. Let's look at customer number 2. Customer number 2 is 3, 6, 25. So 3 Coca-Cola, 6 bread, and 25 eggs. So probably I'll say he is customer number 2. Then customer number 3 is 0, 0, 5. So I'll say customer number 3 is this guy, 0, 0, 5. So what you're actually doing is, guys, we have 3 vectors, okay? Number 1 is this one, number 2 is this one, while number 3 is this guy here. We are basically trying to understand the similarity between these people. That's all. So the first guy is very similar to 2. You can see that the vectors are very close to each other. The theta between them, the dissimilarity between them is not so much. There's a lot of similarity between them. So 1 and 2, they will fall into a single group right now. While when you compare 1 and 3, right, you can see that the first customer is here, while the third customer is here. There is a lot of dissimilarity between them. So I'll call that the second customer is, or the third customer is basically belong to a second group, because he's not so similar to the first and the second guys. He's very dissimilar. So he'll be called as the second group right now. This is exactly what we're doing in typical recommendations and all. So when you look at recommendations, right, you try to create something like this. Hey, this is user 1, user 2, user 3. How are they similar? I think these two guys are similar. Okay, so what are the other products he's bought? So this guy has probably bought a laptop. He bought 2 laptops. He also might be interested in laptops, so you start giving him recommendations, right? So you're trying to understand data point with data point similarity. That is exactly what we are doing even in this particular problem of market segmentation. So what you are doing is you are saying, I have 6 dimensions here, 6 dimensions. Across the 6 dimensions, I will create each and every vector. So first vector will be Albuquerque. The second vector will be Atlanta. Since these people are very close, I will call them group number 1. While I look at something like New York, they are very, very different. So I'll call this guy as 2. But I see that California and New York are probably having a lot of similarity. So I'll call this guy as 2. Then probably I'll say, hey, I have a city something like, Minnesota, or then I can have a city like, Cincinnati probably. So these two guys are very similar from the other people. So they will become 3 and 3. So between data points, guys, we are trying to compare what is the similarity between them, and you're trying to segment them into different combinations, different basically clusters here. So you don't readily have the target column here, right? So you can't create a supervised model here. It's an unsupervised model because data point with data point, you're trying to understand the similarity. It's an unsupervised learning model that we are going to create. And yes, the model that we are going to use is something called as a clustering technique here. What are we going to do? We're going to be using something called as a clustering technique here. The model that we are going to create is basically called as a clustering model. Why? Because the clustering is going to find the similarity between data points and it will start clustering them together. Okay. So it's not a supervised model, guys. You just have the X. You have the 6 predictors with you. X1, X2, X3 goes on up to X is there. You don't have the target with you, right? So you want to find the data point to data point kind of a similarity and then start clubbing them together, right? So it's not a supervised model, guys. It's an unsupervised learning technique that we're going to use. And the name is basically something called clustering. Okay. Now, speaking of clustering, in this clustering, we are going to be discussing about one specific model, something called as K-means. Okay. So in our course here, we are going to be discussing about one clustering algorithm, something called as K-means. What do you mean by K-means? Let us dissect the name here. Here the K is actually equal to the number of segments or the number of clusters you want to create, while the means is basically a methodology by which you're going to create particular clusters, centroids, etc., etc. Okay. K is what? K is basically standing for the number of segments of the clusters here, while means is basically something called as a methodology he is employing at the back end right now. Similarly, we have somebody called K medians. So once again, it's the same concept. K is going to tell us the number of clusters, while medians is a different methodology you're using at the back end to come up with certain estimations. So the algorithm that we're using here is something called as K-means clustering algorithm, guys. There are a couple of more algorithms also available, but this is most commonly used whenever it comes to clustering. But otherwise, there's something called hierarchical clustering. In that, there is something called agglomerative, divisive, etc. Okay, so we don't typically use those people. K-means clustering is the most commonly employed clustering algorithm here. Okay, so clustering, it's an unsupervised learning model. K-means algorithm is actually speaking the model that we're going to be creating here. Okay, so what we're going to do is, guys, take an example. We assume that we have two predictors and we are looking at a scatter plot for each and every data point here. Okay, so we have x and y, sorry, x1 and x2. Okay, and it's not x and y. So we have x1 here and we have x2 here. We have two predictors. We're taking just the two predictors and we create a scatter plot. The scatter plot of all your data points. You now know that these people should basically get segmented. The question is, should I create a cluster like this, or should I probably create a cluster something like this, or can I probably create a cluster something like this, right? Or can I probably create a cluster which looks something like this? So how do I create this particular cluster is exactly what we're going to be doing with the k-means algorithm right now. So we basically want to call saying, hey, I think all of these people are very similar. Okay, they'll be called as number one. They belong to one cluster. These people are all very similar. They'll be called as two. These people are all very similar. They'll be called as three. So these data points, you're going to find the similarity between them and you'll start segmenting and you will create clusters or cluster boundaries like this, which is exactly what a k-means algorithm is going to do for us. Okay. So the way the algorithm is going to work is, guys, there is a series of steps that you need to keep in mind. Okay, there's a series of steps, a lot of steps. I'm going to keep reiterating this particular algorithm in the sense for every iteration I'm going to add something new. Okay, for now I'll keep it pretty basic. So what we're going to do is, the very first thing that the k-means algorithm is going to do is, he needs this input on how many clusters does he want to create. So he's going to ask the user, okay, hey, how many clusters do you want to create? I am probably saying, hey boss, I want to see 3 clusters. So make use of the data and create 3 segments or 3 clusters for me. Oh, is it? Okay. This is the input that he has taken. Now k-means algorithm will say, okay, what you're looking at is basically 3 clusters, correct? What he is going to calculate for us is something called as centroid. So what is the k-means going to calculate? K-means is going to calculate something called as centroid, or otherwise the center of mass. That is the centermost point of each and every cluster here. So what do we have here? This centroid is C1, his centroid is called as C2, and his centroid is called as C3. So what is the k-means algorithm doing, guys? Let me go back and reiterate. Clustering algorithm, it's an unsupervised algorithm. Why is it an unsupervised algorithm? Because we have a lot of data points here, we just want to find the similarity between the data points. That's it. So how do you find the similarity? You make use of an algorithm, something called k-means here, right? So what is the k-means actually going to do? He's going to go back and create these kinds of clusters. He's going to segment using a particular methodology. He has certain steps to be followed. So if you see a scatter plot like this one, x1 and x2, with all of these data points scattered here, you yourself can ideally see that there are 3 possible clusters, correct? So what is he asking? He's asking, hey boss, how many clusters do you want to create? It can be based on a business perspective, or it can also be statistically driven on how to design the number of k. For now, let us assume that k is equal to 3, guys. Which means you're saying, hey, you can go back and create 3 different clusters for me. Okay, I've understood. So you wanted me to divide the 49 markets into 3 different markets. Okay, don't worry. I'll find the similarities of all of these people. Then I will try to segment them into 3 distinct groups of markets. Right? So today you have it, right? So if you take a financial markets, you say, right? This is the US market, this is the Asian market, where this is like, the Japan market. So you call like different countries or different continents, you give it different names. Same fashion. So Asian markets is what? Singapore, China, India, right? So the same fashion. So you're just saying, hey, I think these people are all very similar. Let us segment them into a particular segment here. So you have given k is equal to 3. So he knows that he has to create 3 different clusters. But to compute it, he needs the help of somebody called a centroid, or the centermost point in each and every cluster here. So what is the first thing that he needs? He needs to understand how many k he wants. That's okay. The number 2 is he needs to basically initialize something called as centroids. What does he have to do? He basically has to initialize something called as centroids. So the way he's going to initialize the centroids, guys, is by using 2 methodologies. Number 1, there is something called as a random partitioning method. Okay, the first methodology you can use is something called random partitioning method. Number 2 is something called as a Fogai method. So there are 2 methodologies by which you can initialize a centroid. Number 1 is something called as a random partitioning method, while number 2 is something called as a Fogai method. Don't worry about the first one. I'm going to come back, as I told you, in the next iterations that we're going to discuss. What is the Fogai method? The Fogai method is very simple, guys. He's going to randomly sample 3 data points and he will call those people a centroid. So what is he going to do? He's going to randomly sample data points and he will call those guys as the centroids right now. That's it. So what is he going to do? He's going to go back and call 3 people as centroids. Example, he is probably going to choose this guy randomly. He'll call it as C1. This guy randomly, he will call it as C2. Probably this guy randomly, and he'll call it as C3. I am taking a safe bet, but it could have been completely random. All 3 centroids could have been picked up from here also. We never know. So he's taking up 3 random centroids right now. Randomly, he's taking up 3 data points. Which means if I go back here, right, I would have randomly chosen Albuquerque as the center, then Las Vegas as another center, and then probably New York as another center. Randomly, I could have chosen 3 people. Okay. So we're just choosing randomly 3 centroids, guys. So these 3 points that I marked are going to be the random centroids that we have taken. Good. What is step number 2? The step number 2 is, using these centroids, you need to come up with something called as clusters. What are we doing right now? We are saying, hey, can you make use of these 3 centroids and start creating the decision boundaries, the sort of cluster boundaries right now? Why not? I can do it for you. The way it will happen is, guys, let us take up one particular data point. I'll call him as the unknown data point. He doesn't know whether he has to be part of C1 or C2 or C3. He still doesn't know, right? So you've taken up Atlanta, New York, and Vegas. The problem is a city like, Albuquerque doesn't know to which particular cluster he has to go into, or a city like, let's say, New Orleans, right? He doesn't know which segment to go into. So you're taking up one unknown data point. And what will happen is, guys, he is going to compare the distance between this unknown data point and C1, unknown data point and C2, unknown data point and C3. So what will happen? This unknown data point will calculate the distance. When I mean by distance, the difference. So this is your centroid 1, this is your centroid 2, this is your centroid 3. Let's say this is the unknown city you have. How far is he from C1? How far is he from C2? How far is he from C3? He's going to compute the distances. So how far is a particular data point from a centroid is the question we are asking here. So can you let me know how far is a particular data point from this centroid? So it will be distance of x1 with c1, distance of x1 with c2, distance of x1 with c3. He's going to compute the distances with all the three people. Then logically what should happen? To the centroid to whom he is closest to, he will get assigned. So he will get assigned to 1 right now. So this data point will become what? He'll basically become part of C1. Similarly, let us take up this data point. He will compare with C2, he'll compare with C1, he'll compare with C3. To whom is he closest to? He is closest to C2, isn't it? So he will get himself naturally assigned to the C2 variable right now. That's all. So what will happen? He'll get naturally assigned to the C2 centroid. How about this particular data point? He'll compare with C3, he'll compare with C1, he'll compare with C2. To whom is he closest to? He is closest to C3, so he'll get assigned to C3 right now. So what is going to happen is, guys, every data point, literally every data point is going to compare with all the centroids that you have. And to the centroid to whom he is closest to, or the distance to whom he is very, very minimal, to that particular centroid, this particular data point will get assigned. What will happen? Every data point will compare their distance from the centroids that you have taken to the centroid to whom they are closest to. That particular data point will get assigned. Hence, what will happen? These people might say, hey, we are all closer to C1. These people might say, hey, we are all closer to C3. And these people might say, hey, we are all closer to C2. That's it. In this particular fashion, what you've done is you've basically created the cluster. So you're randomly taking up the centroid, and then what you're doing is you're assigning the data points to these centroids, and you're creating what is called as clusters right now. So what are you doing? You're creating something called as clusters right now, which is step number 2. And now what I'm going to do is, guys, I think with this, I'm going to kind of, stop here. So I'll just give you an intuition of what will happen next. Okay. I'm not going to deep dive, because once when we deep dive right now, it will get into a lot of details. Okay. So let's keep it simple for today. Let's not have an overload of information. So the next steps are going to be pretty simple. The next step is, okay, using these centroids you have randomly taken, you have created the cluster. I agree. But it need not be the right clusters, isn't it? So using these centroids, you have created your clusters. But these clusters may not be the best ones. It need not be good. Hence, what we are going to do is, we are going to evaluate these clusters. What are we going to do? We are going to evaluate these clusters right now using certain metrics. We have something called as within SS. We have something called as between SS. You're going to evaluate these clusters using certain methodologies. You're going to really ask the question, okay, are all the data points within this particular cluster really very, very closer to them? Are they all very similar to each other? That is called as within SS. If they're too closer, if they're very similar, I'm very happy. But if they're not so closer, if they're not so similar, I'm not so happy. So we're going to evaluate these clusters here. Once you evaluate, you will get a result saying what? No, boss, the randomly taken centroids have not been so good. The evaluation is saying that it is not so good. Now what will you do, guys? You will have to find new set of centroids. So you will say, hey, I think this C1, C2, C3 is not the right. Let us go back and find another set of C1, C2, C3. Then using this new set of centroids, let's go back and do step number 2. Let's create the cluster. Let us evaluate the cluster. Once again, it need not be the best result. So let's go back and create new centroid. For this new centroid, let us go back up, create the cluster again, evaluate these clusters again, but it may not be the best result. So go back and find the new centroid again. For this new set of centroid, go back and create a new cluster, evaluate the new cluster, and then if it is not so good, create the new centroid. It happens as an iterative process, guys. So this particular step will keep happening and happening and happening till a particular stopping criterion is met. So this basically happens in a loop-wise fashion till a particular stopping criterion is met. So what is the stopping criterion? How is he evaluating? How is he coming up with a new centroid? And how is he finalizing that, yes, these are the people and this is exactly how he has segmented? All of these things we'll probably take it up in the next class. Okay. So for now, I want you all to understand just a simple concept. We have already discussed regression. One example is linear regression. We have already discussed classification, which is naive-Bayes and logistic regression. In unsupervised, do we have anything? Yes, you're just getting introduced to something called clustering. What is a clustering algorithm are we discussing here? We are discussing about k-means. What does k and means basically talk about? K is telling you the number of clusters he is going to create. Means is talking about the methodology to come up with new centroid. Okay, means is the methodology by which you're going to come up with a new centroid here, in fact. So means is basically a methodology by which you're coming up with a new centroid. What do you mean by a centroid if you ask that question? Very simple. You may have the data points scattered like this without knowing who is similar to whom. What are we doing? We are saying, hey boss, I need 3 clusters. So 3 clusters means 3 centroids, isn't it? So the centermost point in each and every cluster will become the centroid. So how do I come up with the centroid? In the first step alone, we're going to randomly initialize it. We are randomly initializing the 3 centroid. Using the 3 centroid, we are coming up with the cluster. Then we are evaluating the cluster if it is good or bad. If it is going to be bad, we are coming up with a new set of centroid using a particular methodology. Then we will go back up. We will once again find the clusters for these new centroids. We will evaluate them. If it is bad set of centroids, we'll now come up with a new set of centroid again. Then we will go back up. For the new centroids, we'll come up with a new cluster. We will evaluate them. If it is bad, then go back and find a new centroid. At one particular point, you may find that yes, these centroids are good based on a stopping criterion. That is when the algorithm is going to stop its process entirely. So it keeps doing in an iterative fashion when the evaluation results are very good, when the stopping criterion has been met. When the evaluation results are good, he is going to not find any more new centroids. That is when he is going to stop this entire iteration and he will say that, hey boss, this is my final solution. That's it. So it's a repeated iterative procedure, guys. It's going to happen in an iteration here. So this is more like a skeleton I've given you all. There's a lot of details that we should be discussing here. And then we'll jump into the Excel version of the same clustering algorithm to make our understanding perfect here. Okay. But till here, are you all convinced on what do you think you may be probably achieving using a clustering algorithm? At least a skeleton version of the algorithm. Is it all okay, guys? Following till here? What do you think a clustering is going to do? Yeah? Manjeet, is it okay? Hassan, Srividya, Sanjay? Good to go? Thank you. Thanks, Manohar. Great. Okay. So let's keep it simple. We'll, call it a day. I understand that that NLP portion itself would have been a little too much, right? So I think we'll call it a day, guys. Yeah. So what I'll do is I'll upload all the videos and all the Python CSV files by the earliest tomorrow afternoon. Okay. So some of the videos may take a lot of time to convert. So at least the files, I'll make sure that it's probably available by today night. Okay. Maximum everything should be available by tomorrow afternoon. Okay. Tomorrow afternoon, Indian time I'm talking about. Okay. Great. Otherwise, thank you guys. Thanks all for joining. If there's no questions, we can probably call it a day. Okay, Hari, you want some practice for naive Bayes? Some other use case? Okay, sure. Let me look up for something. But this is a very common use case that people use naive Bayes for. I think many of the email classifiers even today are using naive Bayes. So apart from that, is there anything else common use cases of naive Bayes? Let me check. If there's any data set, I'll just share it across to you all. Okay, great. Thank you guys. Thanks all for joining. Let's catch up next week, another session.